Good morning, boys and girls, and welcome back. Today we are going to start our series of tests on series. Okay, we're going to start picking up a bunch of different tests to see whether a series is going to converge or diverge. And most of our tests, especially to begin with, are going to be convergence tests for series with positive terms only. So, for example, I could use it on a series like this. 1 over n, where 1 plus 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. These are all positive terms, so this would be a good test for this type of series. Quick side note, if the series looks something more like this, and all my terms in the series were negative, you still could use an integral test. You would just factor out that negative, and rewrite it, so it's negative 1 times 1 over n. And now, because we pulled out the negative, all your terms are positive in this series, and you could then use the integral test. What you really can't use this for is if the terms are bouncing back and forth. Some positive, some negative, then we would have to go to a different kind of test. But this, again, like many of our tests to begin with, are going to be for positive terms only. And in this case, we have some extra special rules. Okay, so here is our integral test and all the conditions that we need to have to use it. If f is a positive, decreasing, and continuous function, okay, for x's that are greater than 1, if it's positive, decreasing, and continuous, then the sequence or the series, the terms, the sequence that have the same values of f of x or f of n, in this case, then both the series and the integral are going to both converge or both diverge. The same thing that'll happen to one will happen to the other. Okay? So, if a series / a function is positive, decreasing, and continuous, then what happens from 1 to infinity, that integral will converge, and the series will converge, or the integral will diverge, and the series will diverge. Whatever happens to one will happen to both. So we can, since we know how to evaluate integrals like this, we can evaluate the integral to see if the integral converges, and if the integral converges, then we know that the series must converge, right? But I only, again, can use this if the terms are positive, decreasing, and continuous, okay? For the function, just positive and decreasing for the series. So here's a series and both a function that we've played around with a little bit. I can't remember if we've said what happens with this one yet or not. But we have played around the integral from 1 to infinity of 1 over x dx. And we showed how that is going to diverge back in the lesson for improper integrals. Okay? Go back and relook at that video, or you can see my attached video for that to learn more about this function here. But because this integral diverges, we know that this series must also diverge then. Okay? And this series actually has a special name that we will pick up in our next lesson. I'm going to let that just linger out there and let you, think about that one. A little teaser, if you will. But both of these, because the integral diverges, I know that this series is also going to have to diverge. All right, so now let's use this a little bit. All right, so I want to know if this series is going to converge or diverge. Again, I'm not trying to find the sum of it. I just want to know, will it converge on a sum, or is it going to diverge? So the first thing, again, I think it's going to do is write out the first few terms. When I plug in 1, 2, 3, or 4 to come up with these first few terms, I get 1/2 plus 2/5 plus 3/10 plus 4/17. So we can definitely tell that this is going to be these are positive terms. That's the first criteria, right? That they have to be positive. Also then, I want to show that this is going to be decreasing. This looks to be decreasing as I go along, but I probably should prove and show people that's decreasing. And so again, the way that I can do that is by taking the derivative. If I take the derivative and it's negative, then I know it's decreasing. So I'm going to just switch variables real fast. I'm going to call this f of x just for notation easiness. And now I'm going to go ahead and take the derivative. In this case, we're going to have to use the quotient rule. So little low d high minus high d low, square the bottom, and off we go. I'm now going to simplify it. And when I simplify this, we end up with 1 minus x squared over x squared plus 1 squared. And then if I start thinking about what we're doing, we're using values that are bigger than 1, right? Going from 1 to infinity. So in this case here, for x's greater than 1, if I plug in big numbers that are bigger than, I guess I should say, or equal to 1, that's going to give me values that get smaller, right? I'm going to start with 1, and then I'm just going to subtract larger and larger things. The bottom is always positive since it's being squared, so I can say that for values bigger than 1, f prime of x is less than 0, or this is going to be negative, therefore I know that this is decreasing. So I've got positive terms that are decreasing, and this is a continuous function, so we are good to go on the interval we're talking about. So if this were an FRQ, then I think I'd make sure for certain I would play somewhere, you know, I would tell people, hey, these have positive terms and decreasing, you know, and then I can start my integral test. And so for the integral test, we're just going to look at the integral from 1 to infinity of x over x squared plus 1 dx. In order to integrate this, we're going to need use a little u sub. So I say that u is x squared plus 1 and du is 2x dx. So when we do our u substitution, again, make sure you change your limits, but we would get 1/2 integral 2 to infinity of 1 over u du. And now to integrate that, that would just be ln absolute value of u. All right, so I'm getting a little lazy notational here. I just took the antiderivative, 1/2 ln absolute value of u from 2 to infinity. But I probably, again, then remembering with my notation, and at least I think at this point, even though I was being lazy, I'd throw this limit in here so we could start thinking about what's happening. But you would definitely want to throw your limit notation in earlier if this was, again, a more formal proof or demonstration of the integral test, all right? So don't forget those sort of small details. And I guess maybe if you were just doing this on a multiple choice, you probably don't need to go to the limit notation, but just to remind us, that's what I did here. And so now when I do the fundamental theorem, I get ln of b minus ln of 2. And now when I evaluate the limit as we go to infinity, this becomes infinity minus ln of 2, which would just be infinity. So because the integral goes to infinity, I know that the integral diverges. And if the integral diverges, what the integral test tells me then, because it's a series with positive and decreasing terms, that the series will also diverge. So in this case, both the integral and the series diverges. All right, let's try another one here. Number 2, the series, the sum of 1 over n squared plus 1. Again, you could write out the first few terms. That makes you feel more comfortable, see what's going on. I think in this case, we might even just be able to look at it, and we can tell that, hey, our terms are going to be positive. But I think you definitely need to address that positive issue. And then now you want to make sure that it's decreasing. So to make sure that's decreasing, we're going to look at the derivative. Rewrite it as a function, and just think about it, make sure the function is a continuous function. It is. And then now I'm going to take the derivative to show that it's going to be negative. Be smart when you do this. I rewrote it as x squared plus 1 to the negative first, so I didn't have to use quotient rule. I'm a thinker. And then just don't forget to use chain rule, negative 1 x squared plus 1 times 2x, chain rule. And then I rewrote it, and now I'm going to think about this here. The bottom, again, always has to be positive, so I'm only really going to look at the top. And for values, again, for values that are bigger than 1, for x greater than 1, then f prime of x is negative. And since f prime of x is negative, I know that it's decreasing. But again, I need to make sure that I show that it is positive and decreasing before I can use the integral test. Now we're ready to do the integral. Okay, so again, we're going to look at the integral from 1 to infinity of 1 over x squared plus 1 dx. And hopefully when we go to do this, we recognize that this is the antiderivative of this is tan inverse or arctan. So again, just trying to be halfway good here. Switching to my limit notation, the limit as b approaches infinity of arctangent of x from 1 to b. And so this would be the limit as b approaches infinity of tan inverse of b minus tan inverse of 1. Switching to tan inverse because I didn't have room to write arctan. And if we evaluate this now, tan inverse of infinity, well, that's going to happen at, thinking of my tangent graph, that's going to happen at pi over 2. Minus tan inverse of 1 is pi force. So we get pi force. So this integral does converge, okay? And because the interval converges, I know that the series is going to converge. Now, here's the kicker, though. The series converges, but not at pi force. Okay? The integral converges at pi force, but the series does not converge to pi force. I don't know what it converges to. It's not to the same value. I just know that the series is going to converge. So if the integral converges, the series converges, but not to the same value. Okay? The integral test just tells us if a series converges or diverges, but not what the sum of the series is. All right, here's our next one. Ne to the negative n over 2. E to anything is always positive. For n is bigger than 1, that's going to be positive. So this is always positive. Now to show decreasing, we got to find the derivative. So I'm going to use a little product rule. If I go and factor out e to the negative x, then we end up with something like this. E to the negative x over 2 times 1 minus x over 2. And I know, again, e to the anything, that's always going to be positive. So I really want to think about, is this going to be positive or negative to show that the derivative is going to be negative? In this case, 1 minus x over 2 is going to be negative, but it's only negative for values of x that are greater than 2. Now, this is a bit of an issue because n equals 1. We're going from 1 to infinity, right? But it's only negative for values that are 2 bigger than infinity. What we really care about is the infinity part. You can, the series, whether converges or diverges, if you delete the first few terms so that you can analyze this, that's not going to affect the overall convergence or divergence. So in this case, I would start and I would just deal with the integral from 2 to infinity so that I can, just see whether that integral is going to converge or diverge, and then my series will do the same thing. Okay, the first few terms of a series would affect the sum, but not the overall convergence or divergence of the series. All right, so now I want to integrate this from 2 to infinity. Again, you can do 3 to infinity, anything bigger than 2. That was supposed to be equal to there. And to do this, I'm going to have to use ultraviolet voodoo. I'm going to kind of speed through the integration part of this so we can use more of our time for series talk. But you can kind of look at my work as we go through here. I'm going to select my u and dv. Plug into ultraviolet voodoo. Simplify. And then integrate. Now I'm ready to add my limits back on, and I switch to my more proper limit notation. I can apply the fundamental theorem of calculus, and now I'm ready to think about evaluating this. In this case, when I start to go to infinity, e to the negative b over 2, that's going to go to 0 because it's a negative exponent, so e over negative infinity goes to 0. Here I get infinity times 0, which is indeterminate. So really, I should switch that to the bottom. And I would get something that looks like this, where I get infinity over infinity. So here you could apply L'Hopital's, or we have talked about how exponentials grow faster than polynomials, so I know that this is also going to go to 0. Bottom line is both those terms go to 0, and when I evaluate the back, I get minus negative 4 over e minus 4 over e. So this is going to converge at 8 over e. So, again, that integral converges. Therefore, our series has got to converge. This is not the sum of the series. It's not the same thing, and especially in this case because we eliminated the first few terms. But because the integral as it goes to infinity converges, then the series is also going to have to converge as it goes to infinity. Okay, one last little trick we can throw at you here. Once if I just give you the series and it looks like this. Okay, now we have to write our explicit formula for this and set up our own series notation. I'm going to say it might be real good for you to pause this real fast and try to write it out yourself first, and then you can check yourself. Did you come up with something that looks like this? Hopefully you did. Now, again, I'm going to say in this case, I think we see that all of our terms are positive and decreasing, but we at least must state it. I'm not going to go find the derivative in this case. I think we can tell that it's decreasing, but you should state it. Once you've done that, then you can start to look at the integral. In this case, we are talking about just straightforward u substitution. Antiderivative, we get 1/2 ln absolute value of u from 3 to infinity. Using fundamental theorem, we get 1/2 ln of infinity minus ln of 3, again being lazy with my notation. And so ln of infinity is going to go to infinity. So this is just 1/2 of infinity minus some number, ln3, which is this is just going to go to infinity. So this diverges. So because the integral goes to infinity, it diverges, and therefore our series diverges. All right, boys and girls, see you later.